Okay, let's try to get started right on time today. I'd like to go through a bit more of the sets and functions, all of it. So I'm just going to kind of start where we left off with the convex sets and functions, and then we'll continue with today's lecture on the kind of basics of optimization problems. So, right. So we'd given some examples of convex functions last time. Univariate functions, the summary is that you can pretty much always draw them and then just look at the drawing and see whether you have a convex or a concave function. These guys are important. Quadratic functions we'll see a lot. Just to remind you, quadratic functions only going to be convex if this Q matrix, this quadratic, we call it sometimes this part the quadratic form. So this Q matrix has to be positive semi-definite, and we'll see if that's true in just a second. I'll just remind you of an equivalent condition for convexity based on the second derivative. And on that fact, we know that the least squares loss is always convex, because if you were to expand that out into quadratic, you'd see that Q here for this function is just A transpose A. Right? The term that looks like X transpose a matrix times X, what goes in the middle is just A transpose A, and that's always positive semi-definite. Something that you should feel comfortable with. If you're not, then you need to brush up on your linear algebra. Okay, norms we said were always convex. Basically, just from the definition of norms, applying the definition of a norm, you can check the definition of convexity. Applying the properties of a norm. I meant to say you can check the conditions for convexity directly from the definition. And I talked a bit about LP norms. We kind of skipped over these. Let me just spend maybe like another few seconds introducing these guys, because they'll become important a little bit later. We all know what norms on vectors are. We've all seen LP norms and the L infinity norm, which is like the kind of the limit of the LP norms as p gets larger. This guy right here is called the operator norm on a matrix X. So it's defined as the largest singular value of our matrix X. It's always positive, and it actually obeys the basic properties of a norm. Okay, it's 0 if and only if X is 0 as a matrix. It satisfies positive homogeneity, which means that if I take the operator norm of a number A times X, where A is positive, and that's just A times the operator norm of X, right? Because the singular value of the largest singular value of a multiple of a matrix is just that same multiple of the largest singular value, and also satisfies the triangle inequality. Okay, so if I have the operator norm of X plus Y, or Y is another matrix, that's less than or equal to the operator norm of X plus the operator norm of Y. That one's less obvious, but you can check that from basic facts about singular value decompositions. Yeah?
If X is not a square matrix, does that have an intuitive, I know when it is square, when it's sum of the elements of the diagonal, the trace. I'm wondering if it is not, what it would be.
No, I think you're confusing a bit. So the operator norm is the largest singular value. So even for a square matrix, it would not be the sum of the diagonal elements.
No, I was thinking about the trace.
The trace norm. Yeah, so okay, I'll mention the trace norm now. So the trace norm is the kind of our other go-to norm for matrices, and it's defined as the sum of the singular values. Okay, so here R is the rank of the matrix X. So X has R non-zero singular values. That's another way to look at the rank. And the trace norm is the sum of the singular values. Okay, we're going to see that actually these two are dual norms of each other, just like we have dual norms with LP norms. And we'll define all that precisely in a bit. And we'll kind of get quite comfortable with these. These are going to become important when we talk about both SDP programming, but also when we talk about some applications in machine learning, like, for example, matrix completion. It's going to be important to understand what these things are. So can you repeat your question again about the trace norm? You asked?
When it is a square matrix, it would be equivalent to the sum of the elements of the diagonal, right?
Okay.
And I'm saying that if it is not, is there still a way to calculate it out of the elements of the original matrix?
No. So the trace norm is not easy to compute. It requires us to know the singular values of the matrix. That's, that's maybe going to cause some computational difficulties, but it's still well defined. It's just the sum of the singular values. Yeah. Other questions? Is that a question? No. Okay. These guys we all learned were convex functions. Indicator, support function. Indicator is convex provided that the set is convex itself that we're looking at. And the max function is convex. All things you can check from the definition. Right, so I kind of went through these rather quickly. Let me just repeat them again. So a function is convex if and only if its epigraph is a convex set. That's a property that ties together convex sets with convex functions. And I had mentioned that from this property you can actually derive a lot of properties of convex functions that you know from convex sets. And it's actually how we construct a lot of things for convex functions at kind of a fundamental level. It comes from this property. And the epigraph, just to remind you what it looks like, it's the set you get by taking the graph of the function and everything above. Okay, so if this is my function f of x, the epigraph is, basically everything that lies on the graph and above. And this is not a necessary and sufficient condition for a convex function, but it is a necessary condition. So if f is convex, then its sublevel sets are convex. So if you give me any convex function, and I look at the set of all, say, points x for which that function is less than 1, that's a convex set. For which it's less than 2, it's a convex set. Doesn't matter, you can choose any t, any fixed t, that the sublevel set at t is going to be a convex set. Okay? The converse is not true. If you had all convex sublevel sets, the function itself need not be convex. Who can think of a counterexample? Or an example of that, a function whose sublevel sets are all convex, but the function itself is not a convex function. Yeah?
Square root x.
Square root x, yeah, that's a good example. Right? We could even do something like this. We can reflect the square root x around the x-axis. Okay, so this function has all convex sublevel sets. If I cut it anywhere, like this height, and I ask for the set of all points such that the function is less than or equal to that height, it's just an interval which is convex. All of its sublevel sets are convex intervals. It's not a convex. Right? So we call functions that have convex sublevel sets quasi-convex. Okay, quasi-convexity is a weaker condition than convexity. It's not, a function can be quasi-convex, can have convex sublevel sets, but it need not be convex itself. Okay? Okay, these are the real important guys that I went through really quickly last time. If f is smooth, then it's convex if and only if it lies above its tangent line everywhere. Okay, that's what this is saying mathematically. We must have the property that at any x and at any y, f of y is bigger than or equal to f of x plus the gradient of f of x transpose y minus x. So in one dimension, if f was just a univariate function, it would be this condition. Okay, and that just says that if we were to take any point x and draw the tangent line through x, this gives us the tangent line as we vary y, this side. Okay, that's this guy. This is the point x. Say this is the point y. Okay, then the function evaluated at y must lie above the tangent line. That's all that's saying. It's a necessary and sufficient condition for convexity. Okay, and if we have strict inequality here, that's equivalent to strict convexity. So if f of y is strictly larger than f of x plus the gradient of f of x transpose y minus x for all y that are not equal to x, if we have strict inequality, that implies strict convexity. Okay, so that's a condition that is equivalent to convexity or strict convexity with a strict inequality when f is smooth. Another characterization is based on the second derivative. So if f has two derivatives, it's twice differentiable. then it's convex provided that the Hessian matrix is positive semi-definite at every point x. Okay, so another way of thinking about that, again, it's in one dimension. So this was the first order condition. The second order condition in one dimension is just that f double prime of x must be bigger than or equal to 0. Okay. So from 1D calculus, you remember this means that the function is curved upwards. Okay, in multiple dimensions, the equivalent statement or the analogous statement is that the Hessian matrix is positive semi-definite at all x, rather than the second derivative being non-negative at all x. Okay, it's really the same idea. Now there's a bit of trickery. So when it comes to strict convexity, so this is equivalent to convexity. The second derivative in strict convexity is a bit of trickery. So it is sufficient if the second derivative is strictly positive definite. So let me write that down on my notes so you guys can refer to it. This being strictly positive definite, which means all of its eigenvalues being strictly larger than 0 for all x, this implies that f is strictly convex. Okay, that's true for a function with two derivatives. This direction is actually not true. This direction doesn't hold. In other words, we could have a strictly convex function that actually has the property that it's positive definite everywhere, but not positive strictly. It's positive semi-definite everywhere, but it could actually fail to meet positive definiteness everywhere. Okay, its second derivative could be 0 at some points. Can somebody think of an example of that? Function that's strictly convex, but has the property that at some points has a 0 second derivative.
x4.
Good example, x to the fourth. Okay, so if we take this function, this is strictly convex. You can check that from the first order condition, for example. Okay, its derivative is 4 times x to the third, right, which is increasing function. So it's certainly going to satisfy this property. And on the other hand, its second derivative at 0 is 0, right? It's just some multiple of x squared. So I don't know if I can draw x to the fourth very differently from the way I draw x squared, but the second derivative at 0 is actually 0. It has no curvature at 0. Okay? So, just because a function does not have a strictly positive definite Hessian everywhere, does not actually mean it's not strictly convex. Okay, it's just that this is equivalent. This is only a necessary and sufficient condition for convexity. For strict convexity, it's a little more subtle. Okay, so those two are very useful. And for example, a way to check this statement is just to use the second order condition for convexity. Take two derivatives here. All that's left is q. The Hessian matrix of this function is just q. You guys should be comfortable with that. If not, then just do a bit of linear algebra review. Look at the notes on the course website or anywhere else. And then we can just read off the property we saw 2 slides from now, which says that this is convex if and only if the Hessian is positive semi-definite. But the Hessian is just a constant matrix. It's just q. So it's convex if and only if q is positive semi-definite. So that comes from, for example. Okay, we discussed these guys. Just to remind you, this one's kind of obvious. I can take non-negative linear combinations of convex functions and still get a convex function. These two are certainly much less obvious, especially this one. This one says that I can always maximize a bunch of convex functions in a pointwise fashion and get a convex function. And this one says that I can partially minimize a convex function if it's convex in 2 variables. As long as I'm minimizing, say, one variable over a convex set, the resulting function is convex. Okay? So I can always partially maximize a convex function. That's what this is saying. Of x and s. I can always maximize out over s, get a convex function. I can only minimize out over some of the variables if the function was, first of all, had to be convex in the whole variable x and y. And second of all, have to be minimizing y over a convex set. Okay, so it's more restrictions required for partial minimization. And we saw some examples of that. And then I think the last thing that I have here is some examples about composition. Okay, so if I have a function that's convex and I compose it with an affine function, ax plus b, where a is just some matrix and b is just some vector, then the resulting function is always convex. Okay, that's a nice fact. I can always take, your favorite convex function, compose it with a linear transformation or an affine transformation, and the result is a convex function. In general, composition is a little more tricky. So if you want to check whether or not the composition of two functions is convex, then actually we need to know something about the convexity of those two functions, or concavity of those two functions in the composition, and about actually whether or not the outside function is monotone. Okay, and probably the best way to remember these rules is to think about the chain rule when composing two functions. So let's just suppose that h and g are univariate functions, and I want to know whether or not h composed with g is convex. So the function given by h of g of x is a convex function of x. Suppose that these functions were smooth, I could take their derivatives. Then I can use the second order condition for convexity, right, to try to figure out whether or not this is positive everywhere or non-negative everywhere. And the chain rule, if I just take two derivatives, right, so you remember the chain rule, it tells you how to take the derivative of f of a function h of g of x. If I just apply the chain rule twice, this is the expression that I get out. Okay, and it turns out that from this expression you can basically read off when these conditions imply convexity directly. Okay, so we want to know when the second derivative of our function is non-negative everywhere. So let's look. We want to actually assert both terms are non-negative. This guy is always going to be non-negative, right? So for this to be non-negative, I need to have that h, let's suppose, is a convex function, right? Because then h double prime of anything is going to be bigger than or equal to 0. Okay, so if h is convex, then this whole term should be positive for all x. Okay, so that's taken care of. Take a look at this term. If g is convex, then this should be non-negative. And if h is an increasing function, then h prime should always be non-negative. Okay? So in that case, if I have h being convex, increasing, and g being convex, this whole thing is non-negative, which means that my function is convex. That's the first rule. Okay? If h is convex, and I put non-decreasing, just because it's slightly more general than increasing, but you can think of it as h is convex and increasing and g is convex, then we get that the composition is convex. Okay? The other rules follow from this similar logic. For example, if g was concave, then this is less than or equal to 0, and if h is decreasing, then so is this, so their product is going to be bigger than or equal to 0. Okay, so that tells me the second rule. I can take a convex function that's decreasing and g being concave and still have their composition being convex. Okay, so even though these rules may seem a bit arbitrary, you can always rederive them by just taking the two derivatives of your function f and using the chain rule. I always have to look them up. I admittedly never remember these, so I either look them up or I just make this calculation real quick whenever I want to use them. Okay, but just to be clear, they don't assume actually that our functions are smooth. They apply in general. It's just that this is the logic you can use to remember them. Okay, so those are the general composition rules. And if you want to actually compose, say functions h and g that aren't univariate, then you just have to think about things in a component-wise way. So for example, if h is a convex function and it's non-decreasing or it's increasing in every argument, and g is convex, then the vector composition of h and g is convex. So when you have non-univariate functions, it's just slightly more complicated, though you have to apply everything basically on a component function level. Okay, so those are the rules for composition. Just to remind you, affine composition always works. General composition works if you have, say, two convex functions and the outer one's increasing or some different combinations. Okay, a nice example of a convex function that we return to quite often is it has many different names. Some people call this the smooth max function, or the soft max function, and then the Boyd-Vandenberg textbook calls this the log sum x function. It's kind of a silly name, but it's descriptive at least. So the claim is that if I take a bunch of exponentials, so e to the, say, ai transpose x plus bi, ai is it's just an arbitrary vector, I is just a scalar, and I add them up and I take their log, then that's a convex function of x. Okay, this function approximates the maximum of these linear functions, ai transpose x plus bi. Okay, so there's various ways to see that. So that's why it's called the smooth max. To check convexity, there are various. This is maybe just check that you understand the various ways to check convexity. The easiest thing to do is just to say, well, as long as I prove this is convex, so the log sum of e to the xi is convex, I can get convexity of this original line by just using the affine composition rule, right? Because if I take this function, and instead of passing an x, I pass in a matrix ax plus b, that's exactly what I get out of the top. Okay, where those AIs are just the rows of my matrix A. So I can use the affine composition. That'll trouble because if I had kept the AIs and the BIs in here, then then I'll have to do a bunch of chain rules here when I start taking derivatives. So it just makes the math more complicated. So let's just forget about that and say that affine composition will take care of that. And then you can just check directly that the second derivative matrix, the Hessian, is positive semi-definite. Okay, it's just, in this case, that's the easiest way to check that. Directly compute the Hessian, and I won't go through the details, but it looks like a matrix that's diagonal minus ZZ transpose, where Z is exactly the diagonal. And we can invoke some properties from linear algebra to prove that that's positive semi-definite directly. Okay, so this is something that you can just use from now on, right? An example of a convex function that appears quite often, you can use it from now on. But this is how you might verify that it actually is convex. Okay. So let me jump right to this question. So this is a review of what we did in the last lecture and what I talked about just now. Basically, we gave you a bunch of examples we defined convex sets and functions, gave you a bunch of examples of them, and then we gave you some key properties and operations that preserve convexity. So most of the time from now on, if you're given a function or a set, more commonly a function, and asked whether it's convex, you basically identify a few key atoms in the function that you know are convex, and then you try to use the rules that you know preserve convexity to get at your function. So for example, is this function convex? That's a question that's fair game now that we've taught you all about convex functions. So it would be horrendous to check this from the definition, or at least it would be, not very fun. How could you prove that that's convex, let's say, using some of the techniques we just learned in that last lecture? Yeah?
Well, the denominator A transpose x plus b is convex and concave at the same time. Yes?
Okay.
Then the function 1 over x to the 7 is convex because it's that second derivative is positive.
So I think it's a good start. Slightly easier actually to, let's rewrite this function in the following way. So let's just pull out a minus 7 log A transpose x plus b. So what I did was I wrote this as A transpose x plus b to the power of minus 7, and then I just used the property of log that I can always pull out powers to the front. That'll make things a little bit easier. So let's first address these affine compositions. So we should be able to look at this and say, well, it suffices to check convexity actually of this. Okay, if I could check convexity of that, or maybe I should write this as y. Doesn't really matter. But if I could check convexity of this function, it's a function of x and y, then I just get this one from an affine transformation of variables. Okay, so I don't really need to worry about these annoying matrices and vectors in here. Yeah.
You mean by y, so what is the maximum over x or y? Or
The maximum's over these two terms. So this is a function of x and y. So at any x and y, it's defined as a maximum between this function or that function. Yeah.
And then log is concave, so minus log is convex.
Right? So this is a convex function, and so let's just use some rules we know. Max of two convex functions is convex. It's just a special case of the maximization rule we learned. So I just need to check that each of these functions is individually convex. So we just check this one as convex because, as was just pointed out, log is concave, so minus 7 log is convex. How about this one? Right, norm is a convex function. X to the 5 is convex if I look at the how it acts on the positive numbers, and it's also increasing on that domain, right? So if I think about this function as being, to the power of 5, but only operating on the positive numbers, it's a convex function, and it's increasing. So it's this composition is also convex. So this thing's convex. Okay, so we probably won't have things that look quite this ugly, but it is fair game to ask this question. You can get quite an ugly expression and determine that it's convex just with a few applications of those properties.
Question.
Yeah.
So regarding L1 sparsity, so if we have an L1 function, if the function involves L1 or kind of like a non-complex form of it, how would we actually use, for example, the second order IQP point?
I think the question was, how do we check convexity for something like the L1 norm with a second order condition? Is that the question?
Well, yeah, if you use second order condition, then we need to make sure that it's actually twice differentiable.
Right.
Sometimes when we are using a lot of sparsity involved in a function, it might not.
Right. So the second order condition only applies to twice differentiable functions. It says nothing about the L1 norm.
So what happens at the kink in like a proof? Like if you, for example, if you can use the second order conditions on other domains, and then it's
That's not valid. So you have to, the function has to be differentiable, which means that its derivatives find everywhere on its domain. In fact, it has two derivatives. So when we say a function is twice differentiable, we mean that at every point on its domain, it has two derivatives. So it excludes things like the L1 norm, which don't have a derivative at 0, for example. So the second order condition just doesn't apply to things that aren't twice smooth. Okay, so we have, like for the L1 norm, we know it's convex because it's a norm. So we can just use the definition, for example, of the triangle inequality and the other properties of norms to prove it's convex. We can't use the second order condition. We'll learn in a couple lectures, maybe 3 from now, about subgradients, which are like, I want to say replacement, but they're like a version of gradients for non-smooth convex functions. So you can still talk about something like gradients for non-smooth convex functions. But second derivatives, you can't really talk about them. Right. I think that was good to kind of work through some of those details because we were kind of rushed last time. Hopefully I can still get through today's lecture. So we're going to talk about terminology and properties of optimization problems. And then a bunch of transformations that you can make to optimization problems doesn't change their solutions. So I like to give this lecture at the start because I think a lot of this stuff is things that people find natural or some people already know, but to be explicit about it I think is a very good thing because lots of points throughout the course we'll be changing optimization problems in ways that are subtle maybe, and preserve the solution, but it's good to just go out and kind of say those are legitimate equivalent transformations. So we've already defined an optimization problem. Just to remind you what a convex problem is, it's one in which the criterion and the constraints are all convex, and you have the inequality constraints are all convex, and you have linear equalities. And we sometimes call that a program rather than a problem. So I mix the word, it's a convex program or a quadratic program or a semi-definite program rather than an optimization problem. And we often don't write the domain. I often write just minimize over x. I'll forget about the domain. It'll be kind of implicit. So if, for example, f of x is log, it's just kind of implicit that x can't take on the value of a negative number or 0. Okay, then it's going to completely. But if you wanted to be 100% precise, we're only looking at x that are in the common domain of all the functions f and gi. F is called the criterion or the constraint function of all the functions. So all the inequality constraints and all the equality constraints. Then it's called a feasible point. I already learned that bit of terminology. The minimum of our criterion over all possible feasible points is called the optimal value of the convex problem, or sometimes it's the optimum. And it's written, we usually write it as f star. Okay, so if we don't kind of define this later, but f is the criterion, we mean it's the optimal value of the convex problem over all the feasible points. So it is the value of f of x at its minimum when I respect all of the constraints. If x is feasible and f of x is equal to the optimal value, then of course x is called a solution or optimizer. Okay, we sometimes call x itself an optimal point. Okay, but I'll usually use the word solution. And often I'll denote a solution by x star. Okay, I guess I didn't write it here on the slide, but it depends on the context. Sometimes for statistics problems and machine learning problems, I'll use a little different notation, but in kind of some of the more abstract optimization programs we look at, I usually use x star for the solution. Okay, so don't confuse x star with f star. They're different things, right? This is the value of the criterion at the minimum. This is the value of x that minimizes the criterion. Okay. If x is feasible and it has the property that f of x is less than or equal to f star plus epsilon, then we call it epsilon suboptimal. It's just a bit of terminology we use. If x is feasible and the inequality constraint gi of x is equal to 0, then we say that it's an active constraint at x. If gi of x is strictly less than 0, then it's an inactive constraint at x. It has to do with whether or not basically you are right at the boundary of that constraint at x or not. Okay, just a bit of terminology. And this one is, again, an example of something that I think is fairly natural, and probably most people know this already and have already used this, but it doesn't hurt to make this explicit. I can always take a convex minimization problem and recast it as a concave maximization problem. Right? Minimizing f of x subject to a bunch of constraints is equivalent to maximizing minus f of x subject to a bunch of constraints in the sense that their solutions are the same. Okay? The optimal value of the criterions are different, right? This one's going to have the negative optimal value of this, but still the solutions are the same. Okay, the solutions are changed, which means that we'll often write down a concave maximization problem, and in a slight abuse of terminology, we'll say this is actually a convex optimization problem. What we really mean is that it can be reposed as convex minimization. Okay, so I'll call both of these convex optimization problems, even though that one's a concave maximization problem. Right, so if I have a convex problem, then the solution set to the convex problem is written using the notation argmin. And I don't really use this notation super often, but I still think this is a good thing to see. Capital X opt you can write as the set of all solutions to the convex problem. So it's all the values of x that minimize f of x subject to the constraints. And one key property of convex problems is that their solution sets are convex. Okay, that's a very nice property of convex problems, which means I can't have, so, okay, let's back up for a bit because I think people sometimes confuse what we said with uniqueness. So earlier we proved that here, I have actually a few slides later, that convex problems don't have strict local minima. So in a sense that means that if you have a point that's locally optimal, it must be globally optimal. That doesn't mean that there's only one solution. Okay, there could still be multiple solutions to a convex optimization problem. This means that we can't have something like this. Okay, we can't have a point being locally optimal but not globally optimal. It doesn't mean the solution is unique. For example, here's a convex function that does not have a unique minimizer. Okay, I'm trying to make the function flat here. Okay, it's minimized at any value in here. Okay, each of these are globally optimal. Okay, so don't confuse the idea that things don't have, that a convex problem doesn't have a strict local optimum with uniqueness. Those are two separate claims. So what this is saying is that a convex problem always has a convex solution set. Okay, so here's a convex function. Its solution set is anything, let's say, between here and here. These are all the things that, there's no constraints. We just want to minimize this function. This is its solution. That's where it's minimized. It's a convex set. And we can prove that directly from the definition of convexity. This proof is very similar to what we did already to prove that there are no kind of strict local minima problems. Just check that if I have two solutions x and y, then if I take the convex combination tx plus 1 minus ty, that's in the domain. It meets all the inequality constraints. It meets all the equality constraints. This is the exact same logic that we used before with our previous proof. And here, by convexity of the criterion, if I evaluate the criterion at this point, it's less than or equal to t times f of x plus 1 minus t times f of y. But each of these are just f star, because x and y were solutions. Okay, so that means that at this point, the criterion value is also f star. Okay, because it cannot be lower than f star, because that's the smallest it can possibly be. And here we proved that it's less than or equal to f star. Okay, so this is just a very quick check that tx plus 1 minus ty is also a solution. Yeah?
Are you assuming f is continuous, or does that follow from convexity?
It's a good question. I'll just repeat it more loudly. So the question was, are we assuming that f is continuous, or does that follow from convexity? I have not assumed explicitly that f is continuous, although convex functions are always continuous on the interior of their domains. So it's just a kind of fundamental property of convex functions. If you take a convex function, you look at the interior of its domain, it has to be continuous on that set. And yeah, for that you can probably look at the Rockefeller book. I'm sure he'd have a proof of that. Good question. Okay, so that's a property of convex optimization problems. Here's another really important property of convex optimization problems. If f is strictly convex, if the criterion is strictly convex, then the solution set is a singleton. It only has one point. Okay, so if I'm trying to minimize a strictly convex function subject to any number of constraints, of course they have to be of this form, then the solution is unique. The solution set only has one element. Okay, and in that case, when x opt only has one element, we usually don't think of x opt as a set. I'll just write the solution as being equal to the argmin. Okay, so its notation is a bit loose there. We don't think of it as a set with one element. Typically, we just write it directly. The solution is equal to the argmin. Okay, to check this, you can just go through the same logic, except for here, you're going to get a strict inequality. Okay, if t is between 0 and 1. Which means that if there were two solutions that weren't the same, you'd get a contradiction. Okay, because you'd find that a convex combination of them has a criterion value that's strictly smaller than f star. Okay, so that's the proof of that statement. You can go through that in a bit more detail on your own if that wasn't. Okay, but a very important property to remember. Strictly convex criterion for a convex optimization problem means a unique solution. So let's go through a few examples of convex optimization problems and just kind of like read off of what a lot of these things are and ask some questions about them. So I don't think we talked about this problem yet in class, but we'll see it quite a bit. It's a common problem people look at in statistics and machine learning, the lasso problem. So it's a task in which we want to, say, regress some target y on some variables x. X is a column. The columns of x are our variables. So if I didn't have this constraint, if this wasn't here, this would just be least squares regression, right? Just find the coefficient vector beta that makes x beta y the best and the squared error. But here I'm adding a constraint that the L1 norm of beta should be smaller than or equal to s, and s is just some tuning parameter. Okay, so s is fixed here with respect to the optimization problem. It's just some constant. People who've seen, you probably see this in 701, right? In 715, I guess you guys see this. Do you see this in 701? Yes? Okay, that's good. So this problem is one that's kind of popular because this constraint actually enforces sparsity in the coefficients. So what we get at the solution, especially if s is small, is that these weights that we're going to assign to the columns of x, these coefficients, a lot of them are 0 at the solution, which means that we don't actually use that variable at all in trying to kind of predict y. Okay, that variable we are announcing is irrelevant. If I'm going to take a linear combination of the columns of x, I don't have to even use one column, for example. So it's a way to do variable selection. So we'll see this multiple times throughout the semester. I'm not going to give a huge amount of motivation for this for support vector machines. I'm just going to assume these are problems you guys are more or less familiar with. If that's not the case, then you should check out some of your ML notes or come talk to one of us in our office hours. So let's ask some questions about it. So is this a convex optimization? It is, right? Because this is always a convex function. So first of all, the variable here is beta, so we're minimizing over. It's always a convex function because the least squares loss is always convex. It's a quadratic, and the matrix in the quadratic is x transpose x, which is positive semi-definite always. So it's always convex, this criterion. And this is a convex constraint. It's a convex function being less than or equal to a constant. So it's just a, I can think of it as this convex function minus s, which is still a convex function. Remember, s is just like a constant, is less than or equal to 0. Okay, so that's good. The criterion function is this guy, the least squares loss. The inequality constraint function is just the L1 norm. I only have one of them, right? I have G1. So in this notation, I just have one inequality constraint function, and that's the L1 norm. And there are no equality constraints. Sorry, I have, just to be clear, I have one inequality constraint function, and it's actually the L1 norm minus s. Okay, that's my constraint function for the lasso. Right, because I have to have the function be less than or equal to 0. That's how I would rewrite this constraint. And there are no equality constraints. Okay, there just are no equality constraints for this particular problem. The feasible set is just the set of all points that satisfy this L1 norm bound. So we sometimes call this the L1 ball. That's the feasible set. Let's ask about uniqueness in two cases. So the first case, let's suppose that x is full column rank and n is bigger than or equal to p. Remember, x is an n by p matrix. So x is n by p. X transpose x is p. Okay, and I'm telling you that x is full column rank, which means the columns of x are linearly independent. Is the solution unique in that case? Yes? Why is it unique? Right, because I can use the second recognition, for example, for convexity, and I can check that this guy, so x transpose x being strictly positive definite, is equivalent to x being invertible. It's equivalent to x having linearly independent columns. Okay, so these should all be things that you're comfortable with. If I tell you the columns of X are linearly independent, that's another way of just saying that has full column rank. It's the same thing as it being strictly positive definite. And so if I were to check the second order condition for convexity, that means that the criterion is strictly convex, okay, which means that that the solution is unique. That's what we learned right here, right? If I have a convex criterion for a convex problem, the solution is unique. Okay, that's nice. How about if P is bigger than N? Is the solution unique? How many people think yes? The answer is still yes. Okay, so everyone thinks the answer is no. So why is the answer no?
X transpose X is now like P cross P, but its rank is lower, right? Because one of its dimensions is N. So I guess its eigenvalues would not be invertible.
Right, so if N is less than P, then X transpose X, which is a P by P matrix, is singular, which means it's non-invertible. So we cannot claim that it's positive definite. It is still positive semi-definite. Okay, so then here's now the maybe this is what was tripping people up. This doesn't mean it's not that this is, okay, remember I told you that this function, if in general I take the Hessian matrix of a function and I declare that it's not strictly positive definite, even though it's positive semi-definite, that does not necessarily imply that f is not convex. Remember we learned that if the Hessian was strictly positive definite everywhere, that implies that f is strictly convex, but not the other way around. But this is a case in which actually this being singular, we can say directly that our function is not strictly convex. So let's just write this out. Okay, so there are, it doesn't really matter what the cross term is. Plus a constant. So this is our function. And if X transpose X is singular, that means that there are vectors beta that are non-zero that have the property that X transpose X times beta is just 0. Right? That's what it means to be singular. So that means I can find some direction beta that's non-zero that makes this whole first term 0. Which means that along those directions, the function is just linear. Right? All I have left is a linear term in the function. So it's definitely not going to be strictly convex, right? Because in those directions, I just have a linear function. The quadratic term completely disappears. You can check that in more detail if you'd like. Just think about taking beta not equal to 0 with x beta equals 0. And then assert from this that it's not strictly convex by using that particular beta. Okay, so in general, if p is bigger than n, I don't have a unique solution here. Okay, what we'll see later in the course, which is I think quite surprising, is that many cases, arguably most cases, in which most data instances that are high dimensional, we still get a unique solution with the lasso. And we can actually check that straight from the KKT conditions. So that'll be something that we may do as an exercise later. So it's, I guess the answer should be, we say it's unique because we can't establish strict convexity, right? So we put our hands up and say, we don't know. The solution's probably not unique, but we don't know at this point. I'll let you think about how our answers would change if we change the criterion a bit. We won't go through that part. But if we change the criterion to Huber loss, which is just takes basically the squared error loss and clips it, so that at some point it just becomes linear. Huber loss looks like this. So instead of having a quadratic function that just kind of continues to shoot up, Huber loss just linearizes it at some point. That was not the greatest drawing, but I think you get the idea. Okay, Huber loss still. What did I just do? Sorry. I'll wait for this guy, I guess. So Huber loss is still convex. It's you basically clip the function at some point and make it linear rather than making it letting it continue on as a quadratic. But we do it in such a way that the function is still convex. This is the formal definition of this function. It's just called rho on the slides. And this is sometimes in statistics in order to make the problem more robust against outliers. Okay, so if we have points that fall really far away from the linear trend, then the solution is not swayed too much by that. Because with the squared error loss, these residuals would look huge, and so we kind of forced to try to move the regression line to capture them. The Huber loss is a robust problem. Okay, so I'll let you think about how the answers changed if that was a loss instead of least squares. There was a question up there earlier, was there? Yeah.
In this case, if you put C equal to 0, then can you get many solutions?
Sorry, if I put what to 0?
If you want many minima in this case.
Which case are we talking about?
Okay.
Yeah, lasso with this
That's right. But you said the constant C equal to 0.
C.
Well, the one that you've written in your notes on the left-hand side.
Yeah. This constant is just y transpose y. It just didn't depend on beta, right? That's just, I just wrote it as a constant because it didn't depend on beta. What was the question? Sorry.
Yeah, then if there's a vector that's in the kernel of X, then adding that to the solution wouldn't change the value, but would change the solution, giving you many minima.
I didn't really understand. Sorry. If there's a vector in the null space of X, then yeah, we can add it. It would not change the criterion. Correct.
And that can give you many minima.
Well, not clear. I mean, but what we were trying to do is check whether or not we could find that whether F was strictly convex or not. Okay, so if F is strictly convex, that implies uniqueness. If F is not strictly convex, we can't say anything about uniqueness at this point. Okay, and in general, it's more like a case-by-case basis. So that's all we were trying to do here, was to check whether this was strictly convex. And it's not when X has a null space. But I think what you're maybe suggesting is that even if X did have a null space, we haven't kind of constructed the existence of we haven't shown the existence of multiple solutions. And you're right, as I was kind of foreshadowing, the lasso actually does not have generically a non-unique solution even when P is bigger than N. It just happens in kind of odd cases. So, other questions? Okay, I hope that bit was maybe confusing about like it's actually unique in this case. Just forget I said that. We don't know whether it's unique in this case. We may revisit that later, of course. Just something that we could revisit. Okay, let's do SVMs and then we'll take a break. So SVMs are another kind of popular problem that people study all the time in machine learning and statistics, more machine learning. It's a way to produce a classifier. So this is a way to produce a linear prediction function. And this is now a way to produce a linear classification function. It's linear in the sense that the decision boundary is still linear in the variables. That's all I mean by linear. So again, we have a similar setup in that we have an n by p matrix of variables. Each column is a different variable. And now y is also, again, a vector of length n, but instead of being real valued, it just takes, each component takes the value -1 or 1. So it's like the label. Maybe it's two labels that we could possibly associate to any particular object in our training set. The machine problem is as follows. So there's 3 variables. There's really only 2 variables, although I've written an intercept. So you can kind of ignore beta naught if you want. It's just an intercept. It's a single dimensional parameter. So there's really 2 variables that matter, beta and I always forget the name of this. Is this psi?
Oh, the symbol?
Yeah.
Is that a psi? I sometimes always confuse that with zeta. But that's okay, that's a psi. Beta and psi. And the criterion is just the L2 norm squared of beta times 1/2 plus a parameter, this is another tuning parameter, so it's a constant with respect to this optimization problem. It's like S in this previous problem. We would choose it ourselves as the practitioner. So just think of this as fixed times the sum of the size, subject to a bunch of constraints. Each of these size should be non-negative, and I should have the label yi times xi transpose beta plus beta naught being bigger than or equal to 1 minus psi. So essentially what we are doing is we are given a bunch of points, okay, in feature space, and to each of these points we have a label like +1 or -1. Okay, and we are trying to find essentially just a linear decision boundary defined by x transpose beta plus beta naught. That just defines, on either side just defines a half space. So we're trying to find a hyperplane to divide our space, maybe like this, for example, that best separates our points according to this criterion. Okay, and this criterion just allows for a little bit of slack. So instead of, if we had these all being 0, it would be saying that basically the points lie on the correct side of the decision boundary. We get all the +1s on one side, all the -1s on one side. These are called, sometimes in the context of SVMs, they're just called slack variables. We're allowing essentially for a little bit of slack. Okay, so we'll revisit SVMs a few times throughout the semester. That wasn't really an explanation as to why we use them or how they operate. I'm assuming you've seen them in previous courses. But this is a very common problem that people solve. Let's ask the same questions. Is it convex? Yeah, it's convex because the criterion is just a quadratic plus a linear function. It's certainly convex. These inequality constraints are all okay. It's just I can rewrite it as, if I wanted to, I could write it as minus psi I being less than or equal to 0. And this is definitely a convex function. I mean, it's affine. Same with these. I could write this as just one big, inequality constraint of this form. Okay, so those are all my constraints. They're all kosher when it comes to what we're allowed to do in convex problems. Okay, so I think from now on, you can look at this and not even worry about convexity. When you see linear functions on either side of the inequality, and if it's all linear functions, that's fine, right? Because you can always rearrange them in a way that makes them convex constraints. Okay, yeah?
+1 minus psi I?
Yes.
+1, yeah. Thanks. Okay, so criterion, constraints, feasible set, let's just skip that, you guys off. Uniqueness. Is the solution unique? So look what I said, is the solution beta naught psi unique. That's we solve for basically a triplet of variables. Is this unique at the solution? I mean, we should just be clear, it's not equivalent to that, but the criterion being strictly convex is pretty much all we know at this point. If the criterion is strictly convex, then we can say it's unique. If it's not, we don't know what to say. We just can say it's possibly non-unique.
If we set beta to 0, then it becomes linear.
Right, so it's definitely not strictly convex because it's a linear function of size, right? So I don't get the strict convex property. If I hold, for example, if I try to check the definition of strict convexity and I hold these two constant, and I just vary the psi between two different triplets, then it's just linear in that direction. So I definitely don't have strict convexity. So I cannot conclude from what we know that this triplet is convex. Okay? Here I ask what happens if we change the criterion to something a bit weird. So you can think about that. This is another interesting question. What if all I wanted was actually uniqueness of the part determining the hyperplane, beta? Not the slack variables, but the part determining the hyperplane. think about that. Think about if, from what you know already, and how you proved that strict convexity implies unique solution, you could just treat one component of the solution, like the beta component. Because in this case, if I fix all the other variables, the criterion is actually strictly convex in beta. Right? It is the squared error loss. So think about if that implies a unique solution in just the beta component to the SVM problem. Okay. All right, let's take a real quick couple-minute break, and then we have just a few more slides to go. Okay, so sorry for making that such a short break. That was too short. I know we all needed more time, but I do want to get through most of this, if not everything, before we finish. So this property you guys all already know. We won't go over it again. It's such a property that I wanted to put on the slides again. Now let's get into some of the stuff we can do to convex optimization problems. So the first thing we're going to talk about is rewriting constraints. So we can always take a bunch of constraints that we write as, gi of x less than or equal to 0 for a bunch of i's and ax equals b. We can always just encapsulate those constraints into a set C. It's a set of x for which those constraints hold. Okay, so if I say that x is in C, it's equivalent to saying that actually all of those constraints are met. It's just a way of rewriting the constraints. Right? I've called the set of x that satisfy this C, and I've rewritten the optimization problem in this form. Okay, that means that if I ever minimize f of x subject to x being in a set C, that's completely general. That can encapsulate any optimization problem, right? Because I can always think about taking some inequality constraints on functions and equality constraints and just wrapping into this set. Okay, one step kind of even further, I can actually write x being in C in terms of an indicator function. I can define an indicator function, right, based on C, that's 0 when x is in C, and it's infinity when x is outside of C. Remember, we defined that function last time. We even saw that when C is convex, that's a convex function. And if gi, let's start using some of the definitions we know now from convex functions. If gi is a convex function, then the set of all x for which gi is less than or equal to 0 is a convex set. Right? That's a sublevel set of a convex function. Set of all x for which gi of x is less than or equal to 0, it's a convex set. If I assert that this must be true for all I, that's an intersection of those convex sets. Right? So I can write C as, it's going to be the intersection from I equals 1 to m of the set of all x for which gi of x is less than or equal to 0. And I'm also going to intersect that with the set of all x for which ax equals b. Okay, that's convex. Each of these is convex. Intersections are an operation that preserves convexity for sets. So this is a convex set. If I had convex constraints to begin with, C is a convex set. Okay, so for convex optimization problems, I can write them like this or like this, where that's a convex set. And one step further, I can actually convert this constraint into just an indicator function. I can write, I can add to the criterion the indicator function at x of the set C, which is 0 when x is in C and infinity otherwise. That's going to enforce the constraint, right? Because when the constraint's not met, this is going to be infinite. I'm certainly not going to be able to minimize my criterion. When the constraint is met, it adds nothing to the criterion. So I'm just minimizing f. Okay, so these three are the same problem, and they're all convex, right? That's a convex. They're all convex provided that the gi's are convex and f is convex. It's a convex problem. That's a convex problem. This is an unconstrained minimization problem, and this is a convex function because I'm adding together two convex functions. Okay, so in fact, if we are willing to use indicators, we don't have to even ever have constraints lying around. Okay, so it's just a way to rewrite convex problems. A question?
Okay, I was going to ask why ICX is convex.
Okay. So we learned a first order optimality condition for first order condition for convex functions. So it's a necessary and sufficient condition for convexity for a convex function. Following that, in fact, you can prove this in kind of similar ways to the way that you prove the first order condition for convex functions. If we have a criterion that's smooth, we can write down a necessary and sufficient condition for a point x to be a solution to the optimization problem. Okay, so if you give me a convex problem of this form, and remember this is completely general, I can write any convex problem of this form, just, it's all hidden in that set C. And I have a feasible point x. It's optimal, it's a solution if and only if the following condition is met. The gradient of f at x transpose y minus x is non-negative for all y that are in the set C. Okay, so the way I like to think about it is that if you're at x and it's a feasible point and you're thinking about moving to y, you're asking yourself, I'm at x, should I move to y? Is y going to have a better criterion value? Then if the gradient is aligned with the vector from x to y, then that's going to tell you that it looks like the function should increase as I move from x to y, right? Because I'm going in a direction in which the gradient's increasing. So that's a bad idea. So in other words, if this is true for all y, if y I look at, if the gradient is aligned with all steps from x to all feasible y, then you must be at the solution. Okay, it looks like the function should increase in every direction in the feasible set. That's all this is saying, right? Y minus x is the vector that points from x to y. The gradient is aligned with all steps that we could take in the feasible set. Okay, that's a necessary and sufficient condition for optimality, for x being a solution. Okay, we're not going to prove that. The proof is not, I think, very insightful. Find it, I think, Van der Burg. And an important special case is the following. If C is Rn, which means we're not doing constraint optimization, but there's no constraints, so we're just trying to minimize a function, a convex smooth function, f, then we get actually that the gradient must be 0 at x. Right? This can only be true if C was all of Rn, if the gradient was 0. You can convince yourself that's the case by looking at various y's. Okay, remember I can look at all y's because actually C is all of Rn. And that should be familiar from calculus. Right? If I have a convex function that's smooth, I've minimized it if and only if the derivative is 0 in one dimension, or in multiple dimensions the gradient is 0. So an example of this is just minimizing a quadratic. This is a convex function. It's smooth. First order optimality says that I should be able to take the gradient and set it equal to 0, and that's how I can minimize this quadratic. And the gradient of this function, just to remind you, is q times x plus b. So setting that equal to 0, I'm trying to solve a linear system in x. So the linear system being qx minus b. So if q is positive definite, which means that it's equal, then there's a unique solution. This should say x equals minus q times q inverse b. I'm not sure why I got that wrong. If q is singular, which means that it's not invertible, and b is not in the column space of q, then I can never find an x for which qx is equal to minus b. This should say minus b, but I guess that in this case that doesn't really matter. So that means that there's no solution. So this is a case in which I'm trying to minimize a quadratic, and there is no minimum, right? It's minimized somewhere off at infinity. What's an example of that in one dimension? Well, let's suppose q is 0, right? I'm just trying to minimize this function over all of Rn. Okay, so there is a solution that we can write down. And the last case is if q is singular, so it doesn't have an inverse, but b happens to lie in its column space, then there are infinitely many solutions, and they're of this form. Okay, where this is the generalized inverse of q. Okay, so if this stuff is like confusing to you, then again I recommend that you look back at some of our linear algebra notes we have in the course website or elsewhere, and you just kind of do a refresher on what it means for matrix to be singular and all this other stuff. Okay, we're just talking about a linear system. That's all we're talking about. The linear system is qx is equal to minus b. Okay, so these are the cases in which you can or cannot minimize a quadratic, and when it has one solution or infinitely many solutions. Okay, I'll just state this, and then I'll maybe leave it up to you guys to work through it on the slides, and feel free to stop by my office hours or elsewhere if you'd like a formal check of this. If we want to minimize a function subject to equality constraints, we can write down, and this function is smooth, we can write down this very familiar Lagrange multiplier condition. So this is something you may have seen in other classes, like for example, used a lot in physics. So the first order condition for optimality, this guy right here that we learned, in the case of an equality constraint, when C is just the linear space set of all x for which x is equal to b, it actually reduces to this. The gradient of f of x plus A transpose u must be 0 for some u. If I can find an x and a u for which that's true, then I have the solution at x. Okay? And I'll let you, the check for that is basically on the slides. Sometimes we call this, Lagrange multiplier optimality condition. We're going to go through duality in great detail in this course, and we'll actually derive this in a second way at that point, and see a lot more. We can just get this actually straight from the first order condition that we already learned for optimality. Okay, let's see, what do I say in these last few slides? Yeah, let me get through partial optimization and then transformations. So I'll skip over this example. This is just writing out the first order optimality condition for the projection problem onto a convex set, where that's f of x. So in that case, it says something very kind of natural, and we'll revisit projections, or you can read through this slide. So let's go through a few more things we can do to optimize. Partial optimization is one that's kind of quite important. We can always partially optimize a convex problem and retain convexity. That stems from the fact that I can always partially minimize a convex function over some of the variables, as long as what I'm minimizing out over is a convex set. Okay, that was a condition that we learned in the last lecture. So in other words, if I ever have a where I decompose my variable into two parts, x1 and x2, and I want to suppose constraints even separate out between x1 and x2, although this doesn't have to be the case. This is just, I want to write this way so that it's kind of clear. Always minimize out over part of the variables. If I want to minimize out over x2, if I can do that analytically, then I can redefine my criterion function to be f tilde. I've gotten rid of the x2 part, so I just have constraints on x1. And let's say f tilde is the minimum of f of x1 x2 over all x2 for which g2 x2 is less than or equal to 0. Then this problem is convex when this problem is. That just stems from this property up here. So if I partially minimize out over some variables in a convex optimization problem, I still have a convex optimization problem at the end of the day. And a nice example of that is actually what we call the hinge form of the SVM problem. Okay, so I never remember the SVM in this form. That's why maybe I can claim that I didn't remember whether that was a zeta or a psi. I always remember the SVM in this form. I think it's much easier to remember. And in fact, this one is just a rewriting of this one, given by minimizing out over these psi variables. So the first thing that we say is that this right here, this inequality constraint at the solution, this is going to have to be an equality. Okay. This is greater than or equal to 1 minus psi I. I can write that as psi I is less than or equal to 1 minus yi xi transpose beta plus beta naught. So here are my constraints on each psi I, okay, that I have in the problem. So originally I had these two. I can rewrite them like this. And we can say that actually at the solution we have to have psi I being equal to this. Okay? Why is that the case? Wait, what am I? This is completely incorrect. So this is, we get that both 0 this is what I meant. Okay, psi I is actually bigger than or equal to both of these things. This is what I have written on the slides. Psi I is bigger than or equal to the max of 0 and of this quantity. And we can actually argue directly that, in fact, it can't be strictly bigger than these two at the solution. It has to be exactly equal to the max. Why is that the case? Because if it was strictly bigger than either of them, then the criterion is kind of bigger than it needs to be, right? I'm adding psi I to the criterion. So if you give me a proposed solution in which psi I was strictly bigger than both 0 and this quantity, I could always just move it down to either 0 or this quantity, whichever one is bigger. And it would make the criterion smaller, and it would still meet the constraints. So certainly at the solution, I cannot have this being a strict inequality. It has to be an equality. It's just something we can argue directly from first principles. So that means we can actually eliminate psi I. We've basically identified what psi I is at the solution. It's exactly equal to the max of 0 in this quantity. And that's all we've done. We've just rewritten it in this form. This is called the positive part. Just another way of writing the max of 0 in this quantity. Okay, so we've partially optimized. We've gotten rid of psi I. We've identified what it should be at the solution. And this is the form I like to remember for SVMs. You can think of it as some kind of loss function. This is a classification loss function. It's called the hinge loss, plus a regularizer. So it's very similar to a lot of other problems that we know, like the lasso, for example, can be written in a similar form. Okay? Very last thing. Then I promise I'll let you guys get going. So the very last thing are two things that, again, I think are quite natural. But the first is that I can always take, let's say, a monotone increasing transformation of my criterion function and optimize that instead of f. So an example of what we do all the time is, for example, maximum likelihood in statistics we often cast as maximize the log likelihood. Okay, because log is monotone increasing. It's just kind of very natural that I can always either optimize f or a transformation of f as long as my transformation is monotone increasing. And another transformation that's allowed is a transformation of variables as long as that transformation is 1-to-1. So if you want, you can rewrite all the variables in your optimization problem in another way as long as that is a 1-to-1 transformation. So I can change variables from x to, say, phi of y, where phi is some invertible function, as long as its image covers the feasible set, as long as I can kind of get all of the x's I could have gotten in this problem with phi of y. So these are just two things that we will commonly do and won't make excuses for, why either change the criterion by a monotone transformation or we'll change variables by a 1-to-1 transformation. Okay, so that was almost everything. I think I just wanted to get to the fan tope. That was the only thing I missed, so we'll pick up on that next time.